Modern theoretical physics has achieved remarkable success in describing physical phenomena through geometric and field-theoretic frameworks. Nevertheless, one of its most fundamental ontological assumptions has remained largely unchanged: the ontological role of time. Physical persistence is commonly understood as something realized through time, while geometry provides the stage upon which physical processes unfold. This framework explores an alternative possibility. Rather than treating time as the medium through which persistence is realized, it asks whether persistence may instead be fulfilled through something else, with time serving only as the ordering parameter by which change is indexed. If time is not the medium through which physical persistence is realized, then something else must fulfill that role. But what? That question does not immediately suggest an answer. Simply replacing time with geometry is not enough, because geometry, in its traditional role, has generally been understood as the stage upon which physics unfolds rather than as something participating in physical persistence itself. Instead, the question becomes one of progressively narrowing the possibilities. If persistence requires a carrier, then whatever fulfills that role must do so within a coherent physical and mathematical description. That immediately places constraints on the kinds of geometric framework worth exploring. One of the first questions is whether curvature alone provides a sufficiently rich geometric description, or whether geometry admits additional degrees of freedom that might also participate in physical structure. That question naturally leads to torsion as a second geometric degree of freedom alongside curvature. But introducing torsion immediately raises another question. What kind of theoretical framework is capable of admitting it in a physically meaningful way? A minimal Einstein-Cartan theory admits torsion, but torsion does not propagate. That makes it an important extension of the geometric picture, but less suited to a framework in which persistence itself may have an ongoing geometric character. This motivates exploring a non-minimal Einstein-Cartan formulation, in which propagating torsion is also admitted. Once propagating torsion becomes possible, another possibility emerges. The geometry itself may be capable of exhibiting history-dependent behavior. This is where the idea of geometric hysteresis first becomes a meaningful candidate for the mathematical character of persistence, rather than simply an abstract speculation. As the framework developed further, the connection also took on a new significance. Rather than serving only as a mathematical object, it became the natural candidate for the relational and transport structure through which physical relations are maintained across ordered configurations. Contortion then emerged as the means by which torsion is encoded within that transport structure, linking the geometric degree of freedom to the geometry's relational organization. The richer geometric picture also raised a cosmological question. If persistence is realized through geometry rather than through time, should cosmology continue to begin from an exactly homogeneous FLRW background? If the Hubble tension reflects genuine differences in effective expansion between cosmological domains, then an exactly homogeneous FLRW description becomes a less compelling cosmological starting point. That possibility motivates taking inhomogeneous cosmological descriptions seriously. This naturally leads to timescape cosmology, where effective large-scale behavior is constructed from domain-scale geometry through Buchard averaging, rather than assumed from a homogeneous FLRW background. Within the present framework, however, the geometry has already been enriched through curvature, torsion, the connection, and contortion. Since contortion encodes how torsion modifies the connection, and the connection has already emerged as the relational and transport structure of the carrier, it becomes natural to ask whether the averaging procedure should also reflect that richer geometric organization. This leads to a contorsion-weighted adaptation of Buchard averaging. At the same time, the framework no longer treats space and geometry as ontologically separate. The spatial manifold is already geometric from the outset. It is not a neutral container upon which geometry is later imposed, but part of a single geometric spatial ontology. At this point, it became increasingly difficult to identify any single geometric object as the carrier of persistence. The spatial manifold, the connection, curvature, torsion, contortion, and the transport structure all appeared to play interconnected roles. This gradually led to the idea that persistence is not fulfilled by any one geometric component in isolation, but through the integrated geometric structure of the spatial manifold itself. That reinterpretation also changes how matter and geometry are understood. The proposal does not replace the matter-field paradigm with a purely geometric one. Instead, it asks whether the matter-field paradigm is exhaustive. If geometry genuinely participates in the integrated carrier of physical persistence, then it becomes reasonable to ask whether some conserved quantities might also admit meaningful geometric contributions alongside those realized within matter. Angular momentum became a particularly interesting example because its decomposition is already known to be non-trivial. The proton spin problem demonstrates that accounting for the total angular momentum of a system is not always straightforward. The significance of that observation, within this framework, is not that torsion is proposed inside the proton, nor that proton structure itself is being reinterpreted. Rather, it demonstrates that the decomposition of a conserved quantity need not be exhausted by its most familiar contributions. That opens a broader conceptual possibility. If matter need not exhaust every physically meaningful contribution to angular momentum, then the question naturally arises whether geometry may also contribute to the effective angular momentum budget. Within the present framework, that contribution is not sought within nucleon structure. It is instead sought within the effective geometric description of large-scale cosmic structure, where torsion may contribute through its influence on domain-scale geometry. The result is a framework in which a question about the ontological role of time progressively leads to a broader reinterpretation of persistence, geometry, conservation, and cosmology. The framework developed through a process of progressively narrowing the possibilities rather than beginning from a predetermined mathematical theory. Each stage constrained the next, eventually leading to a coherent geometric framework capable of expressing the underlying ontological reinterpretation. The remaining challenge is identifying the mathematical framework capable of expressing that idea. The conceptual foundation has now been established. The next stage is to determine the mathematical conditions, constraints, and geometric machinery through which that reinterpretation can be formulated as a quantitative physical theory.